This is the 14th episode of Advanced J1939. In this episode, I'm going to demonstrate some real failure modes and what they look like on the oscilloscope. So real failure modes with wiring and things like that. As you can see here, I've got a display of in this case, a 250K network, and this consists of an engine controller, some smart sensors, and a fuel pump, and some other devices. So this is a real network. It's perhaps a couple of meters in length, and has 220 ohm terminating resistors on the wire harness. So taking a look at, we'll just take a look at a sample message here from one of the controllers. This device 52, which is 52 in hexadecimal. This is actually an after treatment knock sensor. The source address 0 over here is our engine controller. So there's a couple of devices that are on this network. We can see that we have the acknowledge bit for the messages. We can see some of the other things that we've talked about, the start of frame and the end of frame, this period of time here between messages. So we can see that this looks like a pretty healthy CAN network. There's not a lot of noise. There's not a lot of garbage. What's really good is we've got the difference in between CAN high and CAN low. If we look at one of these messages, so this voltage differential, which is what's really important, right? So this difference between CAN high and CAN low, it looks like CAN high is going during a dominant bit up to 3.6. It looks like CAN low drops down to about 1.4, and that leaves us with 2.23 for the difference in voltage. This threshold, this difference in voltage, which is what the CAN transceivers are looking at, not the absolute voltage reference to ground, but looking at this difference in voltage. The threshold for this to be considered a dominant bit has to be pretty much guaranteed to be, if it's above 1 volt, it should be guaranteed within some limit to be considered as a dominant bit. If it's below some threshold, I don't remember what that is, then it's guaranteed to be a recessive bit. So in this case, our recessive bits are really good. We've got a difference in voltage here of near 0. So this, as I indicated, this is a pretty healthy network. We'll go ahead and I'll go ahead and start this again, and I'll introduce basically a failure mode to the system. We can see right now the CAN bus is running. Everything looks good with the CAN bus. There is some noise here. There is but that's to be expected. It's handled. It's canceled out because we care about the difference. As long as the noise is affecting both CAN high and CAN low, it's not really a big deal. I wouldn't get too excited about it. But I'm going to go ahead and introduce a failure mode now. And this failure mode is one where you're going to see a big change in the CAN bus. And we'll go ahead and pause this, and we'll take a close look at what's going on. So if we look here at one of these messages, let's go ahead and zoom in. We can see that we have, here's our engine controller. You can see the message from the engine controller. Even though this looks like garbage, it's still, CAN is so robust, the signal is still being detected by the other controllers. And we can tell that by the acknowledge bit. We can tell by the CRC being determined to be correct by the other controllers. So even though we've got this problem on the CAN bus, and it's definitely a problem, right? It's really looks like it's probably only mostly affecting the controller, which has this issue. So the failure that I've set in place here is I have put for this particular controller, and we really can't tell which one it is, right? Because we can't, the threshold here is so low, the difference between CAN high is only about 0.4 volts. It has to be closer to 1 volt to be detected. In real practice, most controllers, or at least a lot of the stuff I've worked with, will handle 800 millivolts or 0.8 volts for a difference, but 0.4 for sure, that's definitely too low. So whatever our problem is, it's causing a couple of things. First off, we have CAN high here. Before it was about whatever, we had 3 point something. Now it's 4.16 for CAN high, and that's not necessarily a problem on its own, but it's definitely increased. And CAN low, here's where we've got some real issue with this. So the CAN low is dropped down to a point of about 3.72, or increased to 3.72, whereas before it was down there a couple of volts lower than this. So whatever our problem is, it's causing CAN low to be much higher than it's supposed to be. And so we end up with our difference in voltage between can high and can low being such that we can't determine what's going on. As I indicated, I can't even tell which controller this is because the threshold is so it's below the point where the scope is able to interpret the message. We can see that for sure the messages are definitely being affected by this. It is definitely impacting the bus. As I indicated, most of the other controllers appear to be able to still communicate with this issue for the most part. It may be some errors due to them, but for the most part, it looks like all we're doing is we're losing this controller. Figure out which controller it is. Let's go over to our settings, and whichever scope you're using, whatever it is you're using, you should have a place where you can set for the decoder the threshold. I'm going to drop the threshold down below something below 400 millivolts so that we can kind of tell which controller, or try to determine which controller it is that's causing this issue. So let's go ahead and finish this up, and hopefully there we go. So you can see now, even though the other controllers on the CAN bus aren't able to do this, I mean, they're set so that it's fixed in hardware, I can see that I have a controller with a source address of 12 hex. So this is the controller which is causing the problem. If I were to look at this on the CAN bus, I wouldn't see something which gave me a list of which controllers are on the bus. I wouldn't see source address 12 hex. So let's find out what source address 12 hex is. To do that, we'll go ahead and get the Windows calculator because I want to go ahead and change this. Sorry, I keep everything in hexadecimal. That's what I'm used to seeing. So if I have this in hex as 12, that means in decimal that this is 18. So we go over here to our ISO list of source addresses, which is one of the resources that you do have on the net, and it indicates that this is something related to the fuel system. It's unfortunate that it's not going to give you much more than that, but in this case, the only device that I know that I have on CAN, which is part of the fuel system, besides the engine controller, would be a fuel pump. So I have a smart fuel pump. It's a smart actuator. It's one which is controlled, its speed is controlled via CAN. So this is the device which has the problem. Now, the device isn't the thing which has the failure mode. The failure is something related to wiring. And what I've done here is I've inserted a resistance in series between CAN low and the fuel pump. So basically the stub, the point where the fuel pump would attach to the backbone, if you can imagine the connector, the terminal. So I have corrosion on the terminal. In this case, it's such that it's not an open circuit, but it is high resistance. So a couple of things occur because of this high resistance. It causes a couple of things, as you can see here. One is it caused CAN high, the voltage, to become greater. Okay. The other that it caused, the thing that's really important, is it caused CAN low's voltage to be greater. So if I zoom out and I take a look at one of these messages, what do I see for the voltages on these? Well, I see for CAN high, I have its threshold as let's get one where we don't have both there. We had both there at the same time. Let's go ahead and look at this message. We're going to zoom in on it, and I can see down here with CAN low, it's sitting here wherever it was before, about 1.4, and CAN high is here at 3.6, and our recessive bit is sitting here centered somewhere around 2.5. So whatever it is that this high resistance, whatever's there's a couple of things that we can also detect from this that's really cool. I know that these messages, even though in this case the scope itself, now that I've changed its threshold, it's kind of confusing the scope. You got to think about this a little bit because now I've put other messages. So when you see things like this, where I've got this fuel pump starting to transmit, and then I've got some other controller that's starting to transmit, this is the scope. So if I change that threshold back, and we'll go ahead and do that, I'll go ahead and set it back up to 800 millivolts or so. We'll take a look at it, and what that should do for this message, that should clean that one up, and we can see that that is 52 hex, which I know is one of the NOx sensors. So if I look at this message now, I know that this message is being detected. This message from the NOx sensor, the other controllers are detecting it just fine. And because of that, because we have the acknowledge bit, and because we don't have any errors that were generated by any of the other controllers. The thing that's really kind of interesting is this. I'm going to close this rulers piece. This controller, this source address 12, even though it can't be seen by the other controllers because the threshold is too low, it is apparently still able to read messages from the other controllers, because we can see what's happened here. It stopped transmitting. So it started transmitting a message because the bus was free. It thinks it's putting information out onto the CAN bus, and you can see that it stopped transmitting when it saw another controller start to transmit. So this is basically, it's going to set an error internally. This device would be setting an error, it'd be setting a lot of errors because its messages are being stepped all over. So because of this failure mode, and I'll show this in Circuit Lab and we'll try to explain. It's a little complicated. This is some of the stuff that makes not everybody, I guess, able to do this, to be able to diagnose this kind of information. You really have to know how this works. You have to have a great understanding of the theory of operation of this. And we know that because of the acknowledge bit, everybody else is happy with this message because the CRC is apparently being calculated correctly by everybody. The message is fine. This message from the engine controller, this message from the knock sensor. Really, the only complaint we would probably have on this bus, we might have a few occasional errors, but for the most part, the only complaint we'd have is some complaint about the fuel pump. It may still be working correctly because it's able to see the speed command, but the device, in this case the engine controller that's controlling it, might be complaining that I do not see the messages from the fuel pump. However, the fuel pump is apparently seeing my messages. So whatever it does, and there would be something in the software of the engine controller as to what it does when it doesn't detect that the fuel pump is present. More than likely it's going to just, in this case it's a lift pump, it might be running it at full speed or some speed based on engine load or something. You can imagine it could be anything. I don't know exactly what it's going to be. It's whatever the engineers who designed this system came up with and said, for this failure, this is how we're going to take it. And that failure being, I'm not seeing the fuel pump on CAN. So I'll go ahead and go into Circuit Lab and we'll try to explain what's going on and why we're getting this waveform. Okay, taking a look at the model. So let's say that this is the fuel pump. So this is the device, or this is the transceiver within the fuel pump. This is the backbone. We're going to say that anything where it says CAN high and CAN low, here's my termination. I did put an ammeter in here because I need to show it. We're going to take the two terminating resistors, put them in parallel, and model them as 60 ohms. I have all of the other devices that are on the CAN bus. They are in the recessive state or the listening state. And so what I've shown here to simplify is I have the fuel pump trying to transmit one dominant bit. And so right now I do not have any series resistance, and we can see that our voltages are pretty close to what we see on the scope, 3.6 for CAN high reference to ground, 1.42 CAN low reference to ground, and a difference in voltage of about 2.1 volts. So this is without any problem in place, without a failure mode. And I told you what I did is on CAN low, I put a series resistance in place. So let's set this at something like, I'm going to go ahead and just set it to something really high. So 1,000 ohms of series resistance. A couple of things happen when I do that. We can see that the difference in voltage is about 1.57. Actually, let's make this closer to what I probably have on the failure mode when we have it. So 300, probably about 300 ohms. So let's set it at about 300. When I have it at 300 ohms, that gives me a difference of voltage of about 400 millivolts, which is really close to what we had over here on the scope, right? If we looked at this, what did we see for our difference in voltage here? Well, it was about 400 millivolts when the fuel pump would be transmitting. So there's our about 400 millivolts, 0.4 volts. So you can see that it, as I said, it did a couple of things. It raised CAN high, increased it, but more importantly, it increased CAN low. So why did it do that for? And to explain that, I have to pretty much show you that it's what we call you can't solve this with just Ohm's law. If you wanted to go through and try to solve it, you would have to use something called simultaneous equations with some mesh nodal analysis or something. Or you just use something like Circuit Lab to do all of that hard work for you. Yeah, I used to be able to do that stuff in my head, but not anymore. Not with tools like this. Sorry, I'm lazy. So if I set this back, let's go ahead and take a look at the current that goes through the resistor. It's 35.6 milliamps. That's what we're taking through the terminating resistor. Let's go ahead on the other side here too. I'm also going to throw a couple of voltmeters in because this is important. So if I look at this on the on the other side. So we got our voltmeter here, we got our voltmeter here, and of course voltage has to be referenced to something, right? It can't just be referenced to the air. So I'm going to go ahead and say that here's my values. And of course with with no series resistance, these have to be the same because they're in parallel. There's laws about that. If you don't know that, this is probably a pretty hard step for you. So I'm going to go ahead and increase this up to the 300. As we saw before, I got about 35 milliamps that go through the terminating resistor. So let's go ahead and increase this. And when I do this to 300, a couple of things occur. I have increased the voltage on CAN high. And the reason that I've done that for just a small amount is because I've got a lot less current that's flowing through here now. That means this diode is conducting a lot less, or whatever electronics I have here, and in so doing, it's dropping less, and so I'm getting closer to this 5 volts. That's the reason the CAN high increases. Why did the CAN low out here increase? Well, I'm dropping a voltage. You can see in internal, this looks good. Inside of the controller, as far as it knows, it's transmitting as it should. The problem is I am dropping a voltage across this 300 ohms. And let's go ahead and just prove this. Let's stick if I have current flowing through a resistor, it says I've got to drop voltage on it. So let's go ahead and rotate this guy around where I want him at. I want him right there. And let's take a look to see what we're actually dropping across this resistor. We are dropping 2.5 volts across it. So that says this voltage plus this voltage has to equal whatever this voltage is. And basically, I guess to simplify this, because of the series resistance, I'm dropping a voltage across this. And in so doing, this is the voltage that the CAN does not see. The other devices can't see this. So this is limiting the current that flows through termination, of course. And if I limit the current that flows through the termination, it's all about what the voltage drop across that is. So let's take a look at this. I mean, you could use Ohm's law, you could calculate this, but I've got 6.92 milliamps and 60 ohms. That gives me 400 millivolts. So this current, the fact that I'm not flowing the current that I need through the termination, it can't drop the voltage across it. Therefore, the other controllers, which are all in parallel to this, do not see that voltage. This is not easy. It's not simple. You might have to watch this a couple of times. You might have to go through it a couple of times, but this is how it works. If I were instead to go ahead and if I do this instead and I go the other way, what I will see is it will do the same thing. I put the 300 ohms up here. If I were to take my meter up here instead and we were to drop it across it and see what it's got, I'm going to do the same kind of thing. This voltage is going to be dropped across this guy, and it's backwards because there we go, because I stuck the meter in wrong, but there we go. I'm dropping the 2 volts on the high side now. The scope pattern would be the same, except it'd be different. The scope's pattern would be the same. What we would see is the CAN low would be like this is flipped. So the CAN low would be near its correct voltage, actually a little lower, but the CAN high would be way too low, and we'd have the same issue. The difference in voltage would be not sufficient to be recognized by the rest of the network as a dominant bit. Once again, I apologize. I know this isn't easy, but this is a real failure. This is something that occurs in the field, and I hate to say it, this is why everybody can't do this. It is challenging. It takes a great understanding of theory of operation. If you're going to use something like a scope, you really need to have a good understanding of what you're looking at and why something like this occurs. Why is this message still being interpreted correctly? Why does this look this way on the scope? I think with some practice, with some experimentation, with experience, this stuff will become easier. I've been doing this a long time, and I still get thrown all the time. I still really have to stop and think, and I have to get lucky sometimes and start doing things until I figure out what's really wrong. It's a lot easier after the fact to go through and to show this in Circuit Lab and to be able to explain this on what I see on the screen. That's pretty easy to do now. But if I were in the field and this is the first time I saw this, I would be confused, and it would take me a long time to figure out. Being able to, though, adjust this threshold, this is great. This is for a tool such as this or anything which uses. Otherwise, I wouldn't know which device this is. Once again, I can't find out specifically or exactly. It may not even help me that much if I do this because the device description isn't that great. But for the most part, I know the devices I got on the bus, and in this case, I knew that it had something to do with the fuel system, so I'm pretty much able to narrow it down. It was the fuel pump. Okay, next time we'll go into some other failure modes, and we'll take a look at what those look like on the scope.